Hi, I'm Bill,
And I'm Dave.
and we're here today to do a lab and look at the nature of radioactivity and the effect of time, distance, and shielding materials on various radioactive sources using a nuclear scaler. The first thing we got to do is we got to set this thing up so we can run.
What do you have to do, Bill, to do that?
Well, first thing we want to do is we want to set the voltage. So I'm going to hit the voltage button, and the lab tells me I'm supposed to be at 440. So I'm going to go up till I get to 440. I'm going to hit that again, so that's off. Now, we have to get any background radiation. So there's radiation all over the place right now, right?
Yeah, where does that come from?
Well, I don't know. Where's it come from?
Well, I think our environment, the buildings, cement blocks, radiation from space.
All those things.
All those.
And if you haven't, and maybe you could go look at the cloud chamber video that we also have, so you can look and see what that's about.
Oh, that would be great.
Right? So the next thing we're going to do is we're going to set the time. So we're going to set the time for 30 seconds. That'll be enough for us to get background radiation. And in order to do that, we're also going to put in our holder, since that'll be in there each time we do it. So it's kind of like a control. So we're going to put that in. And then we're going to go ahead and count it for 30 seconds. And we're going to do this 3 times. And why do we do it 3 times?
Do you want that in the first slot or the second slot?
Oh, let's put it in the first slot.
I think the lab says the first slot.
There we go.
Okay.
So we're going to do it 3 times. That way we can get an average, right? That's
Okay.
always good in science. So here we go. We'll count.
So this will automatically shut off then in 30 seconds.
That light will go off in 30 seconds. So the numbers that we're seeing right there are the actual background radiation hitting the GM tube, the Geiger-Moller tube up inside there.
That's the detector part.
That's the detector part, yep.
Okay.
So the first count that we got was 29. So in 30 seconds, we had 29 particles hit that.
That's almost
Detector.
1 particle per second.
Yep.
Should we write that in the data table?
We definitely should. So make sure we write that in the data table.
Okay.
So I'm going to count again.
Now, we don't know what kind of radioactive decay this is, alpha, beta, gamma.
No,
The GM tube doesn't distinguish that.
no, it just knows something hit it. I've heard it explained like a trampoline. It doesn't know the person or the size of the person. It just knows a person hit it.
Okay.
So there we go again. There's the second one. This time we got 27 as our background.
Okay, I'll write that one down.
All right, let's do it one more time.
So the second one was different from the first one.
Yeah,
So these are random events.
very much so, right?
Okay, we got 27 that time.
Yep, so what we had 27, 27, and 29.
So they're fairly close.
Yeah, but not exact.
Okay.
Okay,
So we can average that and get an average.
and get an average.
Okay.
All right, so we're going to go ahead and get ready for part 2 here in just a second. Okay, now we're ready for part B, and this time we're going to use an alpha source. And we're going to put that alpha source in the holder, but we're going to put it in upside down because that little bit of plastic on top could shield the actual source. And when you see the other side, it's got the little metal disc in there. That metal disc is the actual source. So we're going to go ahead and put it into the tray. And then we're going to put the tray in the first slot. And now we're going to count for 30 seconds. Whoa.
That's a lot more than the background.
That is flying. That's a lot of kids jumping on a trampoline.
Yes, it is.
So we'll write that down.
So there's our 30 seconds. We have 851 counts.
All right, so we're ready for our second trial.
So our procedure here is the same as when we did background, except now we have a real radioactive source close to the detector.
Yeah. And these numbers that we're getting, we got to subtract out that average background,
Oh yeah, let's not forget that.
which is roughly 28 or whatever it is based off of what we got.
I always forget to subtract the background. Okay, 883.
That's our second one. Kind of fun to see if it'll get to 883 again.
I'm hoping for 1,000.
Oh, no.
Not quite.
875 for our third one.
Okay, so we'll write that down and then take the average.
Then take the average.
Okay.
And then we'll get ready for part C.
Okay, let's do part C.
All right. So for part C, we're going to use a different source. This time we have a beta source.
And it says beta on there, doesn't it?
It does.
Okay.
How come it's alpha, beta, and gamma and not alpha, beta, and something with a C?
That's a good question.
Okay. So we're going to look at this and we're going to do it 3 times. And we're going to do it 30 seconds, 60 seconds, and 100 seconds. But they're all going to be on the third rung. So we're going to go 3 down. Just like that. Now the first one we're already set to go for 30 seconds, so we can just go ahead and hit count.
You know, Bill, there's probably a reason why we're doing the beta emitter now instead of using the alpha emitter.
Why is that?
Well, that's a good question to ask, but I suspect it has to do with the distance, maybe? I don't know.
Huh.
That'd be something to try and figure out.
So there's our 30-second time, or 30-second count, 1,287.
Okay, I'll write that one down.
Okay. So I'm going to change the time now. I'm going to click time. And instead of being 30, we're going to go to 60. I'm going to hit time again so it goes away. Double check my time. Okay. Okay, so we're ready to go ahead and count for 60.
Okay.
And just for our knowledge, if we hit the time button, that actually is the time.
Oh, so it tells us the real time.
It tells us the time that's
Okay.
going. And I'm going to do that on this one because I don't know if it's going to go to 60, and I want to make sure that that didn't mess up when we did that. And we'll know here in a couple seconds. Oh, good. So it's still counting beyond 30, so it's going to go all the way up to 60.
Okay.
So if I click this again,
Why did it show 40 there?
I don't know. Let's go back to that just to make sure we're...
Oh, that was
because
the
it was
time.
at 40.
Okay.
Yeah. But we can wait. It'll be kind of fun. We can see what our number is once we get to 60. And at 60 it stops. 2,749. Was that double of the last
That's
one?
a little more than double the last time.
Okay. So now I'm going to do time one more time, and I'm going to go up to 100. Oh, that's because that's what it finished at. All right, we're ready to count. So what do we think this might be?
Well, maybe
I'm going to
a
say
little more than 3 times the 30,
So you're saying
and a little less than twice the 60.
so 4,500 ballpark.
I'll say 4,200.
All right,
Let's see who's closer.
4,200 and 4,500.
That's a pure guess. You know, I'm really lucky to have a lab partner that knows what he's doing.
Well, we're at 3.
3,000, 3,200. And where are we on time?
We still got a little bit left.
Ooh, I think we're going to be over 4,200.
Well, I'm hoping we get to 45. 2, 3, 4.
Can I readjust my estimate?
4674. Awesome.
Okay, now we'll take the average of those.
Well, we're not going to do the average.
Oh, we don't do the average.
No. Really, then what we're going to do is answer the questions on the sheet. And then we'll get ready for part D.
Okay.
Okay, so for part D, now we're going to look at distance of this beta source.
What do you mean distance?
Well, how far away from the Geiger-Moller tube, the counter, and we're going to do distance from that to see what happens when we move our source further apart.
Okay, so would we make a prediction about if the source is further from the detector? Does radiation get less the further away, or will we find out, I
I
guess?
think we're going to find out.
Okay.
So according to the lab, we're going to start on the second rung down. So if you want to put that in on the second one.
I can do that.
And it tells us we got to get our time back to 30. So we're going to do our time and do it 30 seconds, and then we're just going to keep moving it down. We're going to do 30 on each rung, going rungs 2, 3, 4, 5, and 6.
So the time is constant, it's the distance that's the variable.
Yep.
Okay,
All
got
right.
it.
So here we go. Let's do the first one.
Now, the last time we did this for 30 seconds with the beta decay, we had about 1287, didn't we?
Right. But we were also on what rung?
We were further away. Okay.
We were further down.
Okay.
So for the second rung, we got 2,951. Now we're going to go down to the third rung. Ready to do our next 30. So are you thinking this is going to be closer to the 1,287?
I'm thinking it should be closer to the, 1,287, which we got in the third slot with 30 seconds before.
Yeah, and this is pretty close.
Yeah, not too far off.
1,427. Now we're on the fourth one.
Yes.
Okay, so 812 on the fourth one.
Well, that's about half of what we got before.
So we got two more. We got number 5 and number 6. Here's number 5.
So it seems like each time we move it down one, the count is roughly half of what it was before.
Huh.
Okay, 557, and the last trial.
So if you're telling me that, then this should be close to 250?
250 or 300?
Or, okay.
You know, I think the alpha particles maybe don't travel as far as the beta particles, which is why we're using the beta instead of the alpha.
Now that wasn't half that time.
No.
Interesting.
Well, it's probably not a linear relationship.
Interesting. Okay, so that's it for part D, and we'll get ready for part E. So I guess on this section, we're going to be looking at how things do when they're being blocked by something. They're being shielded. So the first thing we're going to do, I guess, is we're going to take the beta without anything there, and we're going to do for 30 seconds. So let's make sure our time's at 30, which it is. Okay. So we're going to do our count, and we did the second rung down, right?
Right. I'm in the second rung, or the second slot.
Okay. And then after we get this 30-second, then we're going to add a piece of paper in the first slot, right?
And then we'll see if the particles go through the paper.
Okay.
Do you think they will?
I don't know.
I guess we'll find out.
So 2769.
2769 with
Okay.
no shield.
No shield.
Shield just means something between the source and the detector.
Right.
Okay.
So now let's go ahead and put that, just a piece of paper.
It's plain old paper. Okay.
All right. 30 seconds with the paper. I'm going to say if it is shielding it or at all, it's going to be very little. That's my thought.
So you think the beta particles go through paper easily?
I would think so.
Well, maybe paper doesn't stop them at all.
What was our 2769?
2769.
That's, if it did, it wasn't a lot.
Yeah, it could just be a random difference.
Right.
Okay. So 2665.
So now the lab tells us to go ahead and we're going to use different shields from in here. And in here we've got everything from different size plastics to some metal, some aluminum, and then to some lead. And these are numbered. So this is number 1. And this is just a thin piece of plastic. So we're going to put that in slot 1. And now we're going to see what happens in 30 seconds. Do you think anything's going to happen with plastic?
I don't know. I think the plastic could be more transparent in visible light, but it may not be more transparent with the radioactive particles.
That was a little less.
A little bit less.
25, 25.
Now, are these numbered like from 1 to...
Yeah.
Oh, I see.
To 11.
I see.
Yeah. So this next one is number 2, and it's just a thicker piece of plastic, is all it is.
Oh, I see. So it says here the thickness.
Yeah.
8 mil, 4 mil. Okay. Mil means thousandths of an inch.
Yeah. Okay, 24.6. Wow. Okay, that did a little bit more. Now you're going to see ones that these were kind of transparent through. Now this one's oof. That was a
1924.
little bit of a difference there. So this one's just even thicker. Number 4. This is a fun game, so I think it's going to be like 17. That's my guess. Our last one was 1924.
Mm-hmm. So my question would be, if the thickness doubles, will the amount of shielding double? But it'll be hard to tell because the first two are given in thousandths of an inch. Well, okay, then we can still compare. So this is 3/100ths of an inch. Okay, what do we get? 16?
16, 13.
Again, these may not be linear relationships.
No. Now we've moved to a piece of aluminum.
I think this will make a big difference.
Man, it jumped off counting quick though.
Well, it did. It does seem like a metal would shield more than plastic, doesn't it?
I would think so. Uh-huh.
1352.
So that went down, what, about 300?
A little bit less. What's the next one?
Another piece of aluminum, thicker.
Okay.
That still is mind-boggling that just moves right through that.
Well, matter is mostly empty space, isn't it?
Whoa.
599, that made a big difference. That's about half. Actually, less than half.
And this is our last piece of aluminum, and it's definitely thicker. You can tell the difference of this. So if you think that was half, are we going to be at 300?
I would say we'll be at 200.
200.
That's my guess.
Okay. Oh, it did not jump counting like the other ones.
I'm excited to see what happens when we get to the lead. What do we have, 156?
156. All right, now we move into lead. This first lead is pretty thin, but it still is lead. What? That's hardly counting at all.
Well, how is a lead atom different from an aluminum atom?
Yeah.
It's bigger, has a more massive nucleus.
Man, that is blocking a lot.
And that seems to be much more effective shield.
So
20.
our background radiation was 28. And this is 20. So in theory, it's blocking everything from there and then some, which I guess is possible.
So this is lead again, just a thicker piece.
It's just a thicker, yeah, sorry. Yeah, this
Okay.
is number 9? So, you know what though? I said that about the background, but that was our average. And we've had a lot of radiation out here, so I don't know, maybe data's data, right?
It could be blocking some background.
So that was 26. Oh, this one's definitely thicker. You can even see the thickness on this now.
Now, wait a minute, Bill. That 26, that was more than the previous one, which was a thinner piece.
Right. So I wonder if we've just if we bottomed out and it's just, so it'll be interesting to see if this is somewhere around that same number, right?
Sure, let's check. So the radioactive decay is a random event. This would be like, you know, how many times can you, if you flip a coin 5 times, what's the chance you're going to get 5 heads? There is a chance.
Yeah, see, this was 31.
Mm-hmm.
I think these are all, at least it seems like it, they're all kind of right around the same. Oh man, that one's quite a bit thicker. That's heavy.
Okay, so I have a hypothesis.
Yeah.
I think all we're picking up now is background radiation. I don't think we're getting anything from the data source, because the last 4 measurements have all been in the range of what we got for background.
For background.
You think that's possible?
I think it's your hypothesis. Okay, so now we're going to get ready for section 2. We're going to be now using an alpha instead of the beta. Okay, so this time we're going to use the alpha, and the alpha one we looked at earlier, but here it is again.
It's our polonium-210.
And we're going to do the first one for 30 seconds at the second rung without anything blocking it. Okay,
36.
36.
Now we do the paper. How do you think the GM tube got its name?
Think it's named after somebody?
It could be. How about Mr. Geiger and Mr. Mueller? 40.
Okay.
So that's paper. Let's take that out. Let's try our plastic. So 40 was actually a couple of counts more than the previous one with no shield. That could just be a random effect from background. Okay, 36.
Okay, let's go to the thicker plastic.
So 36 was actually equal to our initial count.
And if 36 and we could take out our background, we're really looking at 7.
Yeah, 6 or 7 counts.
Yeah.
Okay, 26. So that is about the level of background. So Geiger actually discovered this phenomenon of radioactivity ionizing the gas inside the tube back in 1908, about the same time you were born.
About the same time I was born. So that's interesting. That's just a 40. That actually went up, but number 4, just a thicker plastic.
Well, there's some variation here, but these are all in the approximate realm of background.
Yeah.
You know, we've gone from 26 to 40. So maybe all we're picking up is background.
That's a good possibility.
See, there's 26
There's
again.
26. First metal, first aluminum.
So if we keep getting the same value for all these materials, you think we need to do all of them?
I don't know. If not, if we're getting the pretty much background.
Could we conclude that it's just background that we're getting? See, there's 35.
Well, let's jump to the thickest. We're going to jump to the thickest aluminum. See what happens there.
Okay, let's see.
In our previous one, we got to lead. It blocked a lot, right?
Mm-hmm. Yes. $34. So we're bouncing around about the same value.
Okay, so do we want to start with the first lead, or do you want to go to like the second one?
I don't know. Let's just go to the thickest lead.
The one all the way at the end?
All the way at the end. So if this ends up about the same as our previous values, what would you conclude?
I think that we're just getting background.
I think so. So that means the alpha particles are not getting through any of these materials. Even the paper.
Even the paper. Interesting. Okay, well, we're now going to move on to the last one,
That would be the gamma source.
the gamma. Okay, so here's the last one. What are we using this time?
We are going to use a gamma emitter, which is cobalt-60.
Okay. We're going to do the same technique. We're going to start first with nothing, and then we'll do the paper and start looking at the different shields.
Slot 2.
So $5.99.
$5.99. Got it.
All right. Now we're going to put paper in there. Let's see what happens.
So the half-life of cobalt-60 is 5.27 years.
5.27 years.
So would that mean in if we have a new source, 5.27 years from now, the number of counts would be about half?
Yeah.
What do we have, 542?
542. So that went down a little bit, right?
Mm-hmm, a little bit. It may not be statistically significant.
Okay, let's try our first plastic.
$531.
And what was the paper?
542.
Okay, here's a thicker plastic. Now don't forget, and when we put our stuff on the data sheet, we need to make sure we take out the background every time.
Yes.
That's a
See, I forgot that
a
again.
big mistake that we do all the time.
$543.
Huh. That went back up, right?
Yeah, by about 12.
All right. So this is the first one that's not transparent plastic.
Wow, that's even higher. How can that be?
I don't know. 578. Well,
Is that just a random difference?
I guess our data we'll keep taking it and see where we end up. It wasn't as high as our first one, right? 599.
Correct. $604. I can't form any conclusions.
Nope.
So
Me-
far, this is not making a whole lot of sense.
Well, and that's typical in science sometimes, right?
No,
When we think we know what we know, we don't know it.
we'll proceed and see what happens. So is this the first aluminum?
That's the first aluminum.
Okay. And we had 548.
548.
I'm thinking this will start to go down here at some point. 571. It's even more than the thinner aluminum. Are we doing everything right?
You're doing the same thing I'm doing right now, and I'm looking at it. Sure seems like we are.
$540.
Okay, now we're to our first lead.
Okay.
$565. So we haven't got it back up to $5.99, correct? Have we had anything above?
Yeah, we had 604.
Oh, okay. Yeah.
You know, interestingly enough, these shields appear to have no effect at all on blocking the radiation from the gamma source. So could it be that the gamma source can penetrate all of these things?
And the difference in numbers is just because our background is different?
Yes, I'm thinking that. $554.
Well, the numbers don't seem to go slower. I'm watching kind of the speed at which they are being counted. Maybe the last one, the thickest one, will take care of it all.
We'll find out.
So that was 485.
Okay, that's down from 554.
Is that our lowest?
That's 485 is our lowest.
Okay.
Here's the test. Let's try the thickest lead.
It is definitely not counting as fast.
It seems slower. $429. Okay, so that's our lowest measurement.
Okay.
Maybe this is why they use lead for shielding in nuclear reactors.
Maybe that's why. All right. Well, thank you. You can go and answer all the questions on your lab now. Enjoy.